Hello, everyone. My name is Garett, and I'm a math tutor with the DLASC. And today I want to go over a topic that is covered or will be very useful in engineering statics. Okay. And that is how to break things down into scalar components and how to use that. Okay. So let's first start with considering this XY graph, right? This would be our x-axis over here. Right? And this would be our y-axis up here. All right. And let's consider we have a vector, okay? A vector along in this plane, right? Let's say we have this vector here. And this vector we'll call vector f, right? So the idea here is that this vector is going to be denoted as some version of, right, some version of I and some version of A. So like for an example, let's say this was 2 down here. This was 3 up here. This would be, 2I plus 3J. And that's what the vector is. And it has a direction, right? Because we can show that it has some theta here, right? It's pointing so many degrees, from the x-axis. And so we have a magnitude length of this vector, right? This would, if we square root this, we can find the magnitude of it, right? And we have some direction, and that is our vector. But oftentimes, when you're trying to find the resultant, or you're trying to find, its equilibrium, or whatever different kind of problems you're going to work in statics, it's a lot easier to break these two things into components, right? And instead of calling this vector with some theta and some magnitude, we can break it down into our f of x component and your f of y component, right? And it would be just like this, 2i plus 3j, that, those would be our components, okay? And to be more general here, let's say we can write this as ... f equals f of x I plus f of y j. That's a little bit more general here. And, our I direction is going to be our x. So like this would be our I direction, and this would be our j direction. This is, if you've covered vectors, this is kind of a little bit of a review, but this sets us up, because what we can do is we can figure out from our components, we can write, right? We can figure out, if we know our magnitude and we know what it is, we can say that cosine, let's thin this up a little bit, cosine of theta equals, right, f of x, right, because it's adjacent over hypotenuse, over the magnitude of f, right? Because opposite, right, this would be our opposite, or this would be our adjacent, sorry, and this would be our hypotenuse, and this would be our opposite. And because you can think of this as opposite, you're right, this is not a triangle, but you're thinking if you parallel it, kind of like our parallelograms earlier, we can think of this as our f of y also. And so this would also be our O, right? That makes it a little bit more like the right triangle that we think of. But in any case, that would be our cosine theta, and then our sine of theta equals f of y over our f, right? Opposite over hypotenuse. And so if we were to solve here for our f, okay, what we would get is this here. If we were to solve for f of x and f of y, f of x would equal f times cosine theta, and f of y would equal f sine of theta, right? We're just solving for f of x and f of y. This is just algebra. Here, let's go ahead and let's highlight this. This is something that you'll need to know, right? F of x equals cosine theta and f of y equals sine theta, f sine theta. Those are going to be used so whenever you're solving problems to break these down in components, because what you're going to get is you're going to get some type of vector, right? Like here in our example, and you want to break that down in components so you can solve it for solve it easier, right? And you know, this is the formula that you'll use. It'll be the f of x equals f cosine theta and f of y equals f sine theta. Now, this isn't the Bible in the sense that it's not always going to be used like this. It's based on this very this triangle that we've made. But if you're talking about, you know, taking vectors with respect to the x-axis, this will always work. Okay. Now, sometimes you can take it, it might be easier to take it with respect to the y-axis, and then your sine and cosine would change because your adjacent and your hypotenuse would change. Not hypotenuse, but your opposite would change. Hypotenuse would stay the same because it's just the length of the vector. So, you know, but generally speaking, you're going to be trying to find the angle within the x-axis. Now, sometimes they will give you this angle, is like what I was saying, right? Let's call that phi. And if you wanted to know that, your triangle now would become, this would become the adjacent over here, and this would become the hypotenuse. I mean, the opposite, right? But in any case, let's look at an example here to kind of see what I'm talking about. So let's say we have some xy graph, right? Say let's call this as our x. Let's call this our y, or I mean our x and our y, respectively. Right? X, y. Let's say we have some vector here. And we are going to denote this. This vector has an angle of 30 degrees, let's say. And this vector here has a magnitude, let's call it 10 newtons, okay? So we have our newtons, we have our angle. Now we want to try to find the x and y components, okay? So what we would do is to break it down in our f of x, we would use our formula here, right? We would say that this is f, which is 10 newtons, times cosine theta, which is cosine of 30 degrees. And when you punch that into your calculator, you get 8.66 newtons, okay? To find our f of y, we would say 10 sine theta, right? And in this case, this would just be 5 newtons because sine of 30 is 1/2. So we have 5 newtons. Now, here, let me put it in red. Right here, these two things here, the 8.66 newton and the 5 newtons. These are what are called, this is our scalar components. This is what we're talking about here, scalar components. And, you know, if we wanted to put this in vector form, right, now we can find, we can say that F is just equal to 8.66 I plus 5J, obviously in newtons. Okay, but the way we did this, and we didn't have any type of our x-axis, we didn't have anything but an angle and our magnitude. Okay, and instead of making a parallelogram or a tip to tail type of thing, we broke it down into components. Okay, now this really gets very useful when you have to take, let's say we have some graph here and you want to take, you know, we have some vector here, we have some vector here, we have maybe a vector going like this, and we want to find the resultant of these, what we can do is we can break down the components of f, let's call this f of 1, f of 2, f of 3, right? We have 3 different ones, and then we can say all the f of x's, we can sum them together, and we would have, our f1 of x plus f2 of x plus f3 of x. And then we could do the same thing with the y's, right? f1 of y plus f2 of y plus f3 of y. And that, I hope you can see, would just become a lot more simpler than trying to deal with these one at a time. You're just summing them all together, and you can just find the component using, this here, right? F of x cosine theta, f of y sine theta. You're just breaking it down each part, and then you add them together, and then you have the sum of them, and you can have their resultant just right then and there of the y component and the x component, and you can use it to solve whatever you need to solve. But it's being able to break things down in scalar components is going to be probably the most useful skill in this engineering statics class. So my name is Garrett, and happy studying, y'all.